Hi, so my name is Marta. I'm a PhD student here at the University of Québec in Montréal. So my work is on polar laws. I've been working on this for a while now. My supervisors are René Laprise and Philippe Gachon. So I'm going to show you today the case study of a polar law that developed in Norway in 2019. We have talked about polar laws a little bit yesterday in some presentations, but for those of you who don't know what a polar law is, it's an intense mesoscale cyclone that develops at high latitudes near the sea ice and the snow-covered continents during marine cold outbreaks, and they develop during wintertime. And they can be quite intense sometimes. They are associated with severe weather, such as strong winds, which can reach hurricane force in some cases, and also heavy storm showers. And they are short-lived, and they are quite small, so it's important to focus them. And thankfully, now we have high-resolution models, which are better at forecasting polar laws. So my case study was of this polar law here, which made landfall in Norway on the 25th of March, 2019. And here you have an image, an infrared satellite image of this polar law. And the main goals of my research are first to quantify the impact of the initial conditions of the simulation of the polar law, then assess the skill of the developmental version of the convection-permitting Canadian regional climate model at reproducing this polar law, and finally analyze the development mechanisms of the polar law. So I'm still working on the third one, but I have some results. So first, regarding the data sets I used, I conducted simulations with the Canadian regional climate model in non-hydrostatic mode with a time step of 1 minute, and the model has 62 vertical levels and a grid measure of 2.5 kilometers. And I did an ensemble of simulations with like 8 simulations in total, started on the 23rd of March every 6 hours. So the model is the same, I'm just initializing it at different times. And I also use observation for verification of this, the polar law. So I use surface stations and drifting buoy observations. So you have the image there of the locations of the observations. And note that I only use observations within a 300-kilometer radius from the polar law center, because I calculated the size and it was around a diameter of 600 kilometers. And as you can see, most of the observations are on the coast, and I have observations of sea level pressure, temperature at 2 meters, dew point temperature at 2 meters, relative humidity at 2 meters, wind speed at 10 meters, wind gust at 10 meters, and 1 hour accumulated precipitation. And I also use an infrared satellite image from MODIS, AVIHR, and VIIRS, and also finally, of course, I use ERA5. So methodology seems quite simple. So first I had to prepare the data sets. I had to interpolate from the grid model, the variables from the grid model to the observation points. And I use bilinear interpolation for noisy variables and bicubic interpolation for smooth variables. And for the conventional observation, I had to filter them and do some cleaning. And then I verified the simulations. I did first manual tracking of the polar law. So for the observed polar law, I used infrared images to try to find the polar law center. And for the ERA5 and the simulations, what I did was to use the sea level pressure field. And then I computed some verification statistics, so the mean error, the root mean square error, for the wind, it was the root mean square wind vector difference error, and the Spearman correlation coefficients. And finally, I analyzed the development mechanisms using what seemed to be the simulation. So the first question is the polar law represented in the simulations? And the answer is yes, but not in all of them. So you can see an image here of the sea level pressure contours on the 25th of March at 3, which was when the polar law was well developed. And as you can see on the 23rd of March, there's only, regarding the simulations that were initialized on the 23rd of March, there's only one of them which captures a law, but it's almost half the size of the real one. And only 2 simulations of the ones which started on the 24th actually captured the polar law. So the second question is, how well is the polar law represented? So I looked at my simulations that represented the polar law and also ERA5. The summary is that the one initialized on the 23rd, as we have seen, has a smaller size and shorter lifetime. The ones initialized on the 24th that simulate the polar law are pretty similar in size and in lifetime. And ERA 5 is also pretty similar in size, a little bit shorter in lifetime. And then the figure at the bottom shows the sea level pressure at the center of the polar law. So the blue line are the observations, but note that the observations they're not all of them, because I only took the observations that are no more than 25 kilometers from the polar law center. And so as you can see, the simulations that start on the 23rd simulate a polar law that is deeper than the observed one, but this could be because the observations are not necessarily at the polar law center. And ERA 5 has the results that are closer to the observations. And finally, on the right figure, you have the polar law tracks for the observed, again in blue, and then you can see that ERA 5 is pretty close to the track, the real track, and also the polar law on the simulations initialized on the 24th are pretty close also to the real track. So the second question is, how well are the atmospheric figures represented? So I don't have much time, so I'm just going to talk about the sea level pressure, which shows the most interesting results. And the figure shows the scatter plots of the simulated sea level pressure with the observations. At the top are the simulations initialized on the 23rd, and the second line are the simulations initialized on the 24th. And the bottom is ERA 5, and as you can see, ERA 5 does a good job in representing the sea level pressure. And the simulations that simulate the polar law and were initialized on the 24th do a good job too, but they show underestimation of sea level pressure between 1,000 and 1,010 hectopascals. So as we saw in the slide before, maybe this actually means that they simulate a polar law that is deeper than the observed one. And then the other simulations, as you can see, they clearly overestimate sea level pressure. We can see like an arrow-like shape. And as for the other variables, the results are not very different between the simulations, and it's actually a little bit surprising that the simulations that simulate the polar law, so similar or higher aggregate absolute mean error compared to the other simulations. And finally, I'm just going to show the development mechanism, a little bit about what I've learned about the development mechanisms. So this first slide is just to show the characteristics of the polar law with the best simulation, which is the one initialized on the 24th at 6 p.m. So you have the sea level pressure is aligned with the down-looking triangles. And you see that the minimum sea level pressure was reached at 3, and it's a minimum sea level pressure of 996 hectopascals. The maximum 10-meter wind speeds that were reached is 30 meters per second. And it's interesting to see also the surface heat fluxes, which are at the bottom figure. So the orange represents the sensible heat flux, and the blue line represents the latent heat flux. And the continuous line is the maximum, and the dashed line represents the average. And as you can see, the latent heat flux on average are slightly more important than the sensible heat fluxes, and also the maximum attained is higher. So after looking at the fields, these are the preliminary results. So it looks like it's baroclinic development, and this would be the genesis stage at 3 p.m. The figure on the left shows the temperature in colors, and the contours is geopotential height, and all of these variables are at 800 hectopascals. So as you can see, we see the typical temperature field where you have this southward colder advection on the left side of the polar law, and warm northward air advection on the right side of the polar law. And the violet line is the profile that you can see on the right side of the slide. So you can see the vertical profile. The violet square represents the center of the polar law. And you can see that there are 3 places where we have a warm anomaly. And also in these places, we see upward vertical movement, which is especially really strong on the left side. And finally, the final stage is the occlusion of the polar law. And we can see on the left figure that the tongue of warm air is not in the center anymore, and you can see the cyclone is occluded. And again, on the right side, we have the vertical profile of the line represented on the figure. And we see again, there's still, around the center of the polar law, there's still 2 warm anomalies with upward vertical movement, which is now less stronger than before. So the conclusions of this, First, regarding the verification, is that the Canadian Regional Climate Model does represent the polar law, but the ability to represent this polar law strongly depends on the initial conditions. The second result is that ERA 5 has more skill than the Canadian Regional Climate Model at reproducing this particular polar law. So in that sense, we don't see much added value of the model compared to the reanalysis that drives it. Although we can see, for example, that precipitation has more maximum values, higher maximum values in our model compared to the ERA 5, which has a limit of 2.5 millimeters of 1 hour accumulated precipitation. And finally, regarding the development mechanisms, in this case, I see that it's baroclinic development which plays a main role in the development of this polar law. And this is it.
Marta. Any questions for Marta? Ivan.
Thank you. So that's an interesting conclusion that you arrive at here, I think. So did you use observations for data assimilation in starting up the high-resolution model?
Sorry.
So did you include any data assimilation in starting up your model? Because when you have a model that is derived by ERA 5, if you don't have any data assimilation on top of it, you would expect results to mimic much of what already is contained in ERA 5, I suppose.
Yeah, no, I wasn't using data assimilation, no. So
Okay.
I used ERA 5 only.
Thank you.
Oh, sorry. Yeah. So yeah, I didn't use data assimilation.
So that would be an interesting next step, I would suppose, to see if you could get some differences there.
Yeah.
More questions? Okay, then thank you again, Marta.